Welcome to today's presentation. Let's talk about the logistics involved in supporting this rapid growth in electric vehicles. We're looking at an estimated investment of around $445 million to build out the necessary infrastructure. Specifically, we'll need approximately 32,000 charging stations to meet the upcoming demand. By 2030, projections suggest there will be about 15 million electric vehicles on the road. This scale of growth really underscores the importance of planning and investment now to ensure we have the infrastructure to support it. It's a significant but exciting challenge that ties into the broader shift towards sustainable transportation. Let's take a closer look at the electric vehicle routing problem, or EVRP. This is a specific type of logistics challenge that focuses on optimizing routes for electric vehicles. The main goal here is to solve a logistics problem by developing the most efficient route possible. Efficiency is key in this context because electric vehicles have unique constraints, such as limited battery range and charging needs. So, when we plan routes, we need to carefully consider these factors to ensure that vehicles can complete deliveries without running out of power. Overall, the EVRP is about balancing the logistics demands with the operational limitations of electric vehicles, all aimed at creating the most efficient route. This not only helps reduce costs, but also supports sustainable transportation efforts, which ties into our broader theme of innovative and eco-friendly logistics solutions. Let's explore how integrating charging and battery swapping stations can significantly enhance electric vehicle operations. When we talk about the electric vehicle routing problem with simultaneous pickup and delivery, or EVRP-SPD, we're addressing a key challenge: ensuring vehicles can efficiently recharge or swap batteries during their routes. This integration is crucial because it helps minimize downtime and optimizes overall route efficiency. By strategically placing charging and swapping stations, we can support seamless operations, reduce delivery times, and improve service reliability. This approach aligns perfectly with our broader goal of making electric vehicle logistics more sustainable and practical. It's about creating a smarter, more connected infrastructure that meets the needs of modern transportation networks. So, inspired by the multiverse theory, we're exploring the idea that our universe might not be the only one out there. The multiverse, as you may know, is basically a collection of multiple universes. Now, according to this theory, there isn't just one Big Bang that created everything we see around us. Instead, there could be many Big Bangs, each giving rise to its own universe. We often say that the number of universes, n, is equal to the number of Big Bangs, so n Big Bangs means n universes. This leads us to the concept of the multiverse optimizer, which is inspired by these ideas. It's a way of thinking about optimization and problem-solving by drawing parallels from how these multiple universes might work. Now, tying this to the Big Bang theory, which is more familiar to most of us, it suggests that our universe began with a massive explosion, an incredibly energetic event. This explosion marks the beginning of everything we know: space, time, matter. According to this theory, before that event, there was simply nothing. No space, no time, no matter. So, understanding the Big Bang as the origin story helps us see how it fits into the bigger picture of the multiverse idea, that our universe might be just one of countless others starting from their own Big Bangs. This connection is really fascinating because it broadens our perspective on how everything could have begun, and it adds a whole new layer to how we think about the origins of our universe and beyond. Now, let's explore how MVO uses three main concepts from multiverse theory. First, we have the white hole, also known as the Big Bang. This is thought to be created where a collision between parallel universes occurs, serving as a kind of cosmic event that sparks a new universe. It's like the opposite of a black hole, where instead of pulling everything in, it expels matter and energy. Next, we have black holes. These are incredibly powerful objects with such strong gravitational pull that they can attract everything, including light. They act as cosmic giants that can trap matter and even influence the structure of the universe around them. Finally, there are wormholes. Think of these as tunnels or shortcuts through spacetime. They could potentially allow objects or even information to travel from one universe to another, effectively connecting different parts of the multiverse. This concept opens up fascinating possibilities for travel and communication across multiple universes. All these concepts, white holes, black holes, and wormholes, are integral to understanding how multiverse theory connects with the ideas we're discussing today. They help us visualize the dynamic and interconnected nature of multiple universes, which is at the heart of what we're exploring in this presentation. Let's take a closer look at the universe selection mathematical model within the multiverse optimization algorithm. This model is crucial because it helps us simulate the process of selecting the most promising universes, or solutions, from a vast search space. Essentially, it mimics the natural process of universe selection in the multiverse theory, where only the most optimal universes survive and influence the next generation. The key point here is that this selection process guides the algorithm toward better solutions over iterations, by focusing on universes that demonstrate higher fitness or better performance. This is vital for ensuring that the algorithm converges efficiently and effectively to an optimal or near-optimal solution. What's particularly interesting is how this model balances exploration and exploitation. It explores new possibilities across the multiverse, but also exploits the best universes found so far, ensuring a thorough yet focused search. This concept ties directly into our overall theme of optimization. It's about smartly navigating complex search spaces to find the best outcomes. In summary, the universe selection mathematical model is a foundational component that drives the effectiveness of the multiverse optimization algorithm by intelligently selecting and propagating the most promising solutions. Wormholes, as we understand them, act like tunnels connecting a white hole and a black hole. Think of them as shortcuts through spacetime, allowing objects to pass between different regions of the universe. In the context of the multiverse, or MVO as we often call it, it's assumed that each universe has these wormholes. These wormholes enable the exchange of objects, but what's fascinating is that this exchange happens randomly. There's no specific pattern or consideration of the inflation rates of the universes involved. It's as if objects are just moving freely through these tunnels, without regard for the nature or size of the universes they connect. So, how do these universes exchange objects in the MVO? Well, it's through these wormholes that objects can teleport or transfer between universes, regardless of their physical properties or inflation states. This randomness is a key aspect because it suggests a dynamic, interconnected multiverse where exchange isn't limited or constrained by traditional physical laws. This concept ties back to our overall theme of understanding the multiverse as a complex, interconnected system. It shows that the exchange of objects isn't just limited to our universe, but can happen across multiple universes through these mysterious wormholes, making the multiverse more dynamic and interconnected than we might have initially thought. Let's walk through the step-by-step process of the MVO algorithm applied to the EVRP SPDchar datasets. First, we start by inputting the population size and the maximum number of iterations, which are essential parameters for guiding the search process. Once initialized, we evaluate the fitness value, specifically the total distance, for each universe or route in our population. Among these, we select the best universe, which is the route with the minimal total distance. This best route serves as our current optimal solution. Next, for each universe, we update the WEP and TDR parameters, which influence the exploration and exploitation behaviors of the algorithm. To promote exploration, we select one universe using the roulette wheel selection, designating it as the white hole. This process allows the algorithm to probabilistically favor better solutions while still maintaining diversity. For exploitation, we simulate wormholes as tunnels that facilitate the exchange of objects. They're essentially a means for different routes to share information and improve. We then repeat this process, updating parameters, selecting universes, and exchanging information, until we meet our stopping criteria, which is typically reaching the maximum number of iterations. Once the process concludes, we display the best universe found, the optimal route, with the minimal total distance. This approach ensures a thorough search, balancing exploration and exploitation to find the most efficient route in the EVRP-SPDCHAR problem. Let's take a closer look at some of the key assumptions underlying our electric vehicle routing problem. First, each vehicle departs from the depot and returns there after completing its route, which helps us maintain a clear start and end point for all operations. Next, we assume that every customer has a specific demand and a designated time window that must be satisfied. This ensures our routes are not only efficient, but also meet service-level requirements. We're working with a heterogeneous fleet, meaning that each vehicle has different load capacities, battery capacities, and energy consumption rates. This adds a layer of complexity, but also makes our model more realistic, as real-world fleets are rarely uniform. The delivery and pickup demands for each customer are fixed and known in advance, which allows us to plan routes with certainty. Moreover, the total load, both for delivery and pickup, must stay within each vehicle's capacity, preventing overloading. Energy consumption is modeled as depending solely on travel distance, at a constant rate, so 1 unit of distance consumes 1 unit of energy. This simple but effective assumption helps us manage energy planning. Charging stations are designed to provide both battery swapping and recharging facilities, giving flexibility in how vehicles recharge during their routes. The battery consumption of each vehicle is directly tied to travel distance, again at a constant rate, simplifying our energy calculations. Travel time is determined only by distance at an average speed, so we're not considering delays or traffic variations in this model. And importantly, we're not factoring in vehicle operating costs here, which lets us focus on routing and energy aspects. Finally, our model can accommodate different types of fleets, either homogeneous, where all vehicles are the same, or heterogeneous, with diverse vehicle capabilities, and can incorporate stations that provide charging or swapping, depending on the scenario. All of these assumptions help us build a flexible yet manageable framework for optimizing electric vehicle routes in various operational contexts. So, here we see that EVRP-SPDCHAR, which is a key metric in our study, can actually be formulated through an optimization problem. What that means is, instead of just calculating it directly, we set up a mathematical framework that allows us to find the best possible solution under certain constraints. This approach is really powerful because it helps us systematically identify the optimal resource deployment or scheduling strategies. It ties into our overall theme of improving efficiency and decision-making through advanced modeling. By framing EVRP-SPDCHAR as an optimization problem, we gain a structured way to analyze and enhance our processes, leading to better outcomes. In questa slide, Voglio parlarvi del caratteristici chiave del flot eterogeni e omogeni. Innanzitutto, la flot omogeni sono composti di veicoli identici, mentre la flot eterogeni sono composti di diversi tipi di veicoli, ognuno con caratteristici specifici. Per la flot eterogeni, alcuni dei fattori più importanti sono il tempo di scambio del battery, la velocità, il consumo energetico, la capacità della batteria e la capacità di carico. Questi elementi influenzano direttamente l'efficienza operativa e la pianificazione del ROT. In correlazione, CI sono studi come quello di Wang et al., Heyermann et al., Chen et al., e Schneider et al., ci hanno analizzato questi aspetti in diversi contesti. Per quanto riguarda I dataset, abbiamo il dataset di flot eterogeni, ci include dati su clienti, stazioni di energia, e depositi. Questi dataset sono stati utilizzati per analizzare fleet di diverse dimensioni. Ad esempio, Schneider et al. Ha sviluppato un dataset con 36 casi di piccola scala, con 5, 10, o 15 clienti, e un altro con 56 casi di grand scala, con 100 clienti. Infine, il dataset EVRPTW ci si concentra sui veicoli elettrici per il problema del percorso, con limiti di tempo. E grave fondamentale per tester e validare la strategie di pianificazione in scenari realistici. In sintesi, questa slide ci aiuta a capire come le caratteristiche del flot e I dataset associati siano fondamentali per sviluppare soluzioni efficienti e adattabili nel campo dei veicoli elettrici e della gestione del flot. Let's take a closer look at this table, which summarizes the performance of different algorithms across various instances and fleet configurations. First, you'll notice that the table is divided into sections for different fleet types, such as C1, C2, and so on, each with multiple instances. For each instance, we compare 3 modes: BSS, CS, and hybrid. The key metrics here are the average distance, the best distance achieved, the computational time in seconds, and the gap percentage, which indicates how close the solution is to the best known or optimal. What stands out is that hybrid methods generally tend to produce solutions closer to the best distances, often with lower gap percentages, and sometimes in less time compared to BSS and CS. This suggests that hybrid approaches are quite effective in balancing solution quality and computational efficiency. Also, when looking across different fleet types and instances, we see variability in performance. For some instances, the gap is minimal, indicating a near-optimal solution, while for others the gap is higher, showing room for improvement. This detailed comparison helps us understand the strengths and limitations of each method, and it underscores the importance of selecting the right algorithm depending on the specific problem characteristics. Overall, this slide reinforces that hybrid approaches are quite promising, especially when we aim for high-quality solutions within reasonable computational times, which aligns with our broader goal of optimizing delivery and pickup operations efficiently. Let's talk about plotting routes. When it comes to planning effective routes, there are a few key points to keep in mind. First, understanding the most efficient path is crucial, as it can save us time and resources. Next, we want to consider the specific needs of our project, whether that means prioritizing certain locations or avoiding obstacles. It's also important to think about flexibility. Being able to adapt routes as conditions change can make a big difference. Connecting these concepts to our overall theme, designing thoughtful routes ensures that our operations are not only effective, but also sustainable in the long run. So, always approach route plotting with a strategic mindset, balancing efficiency, adaptability, and the unique requirements of each situation. Now, let's explore some key concepts in electric vehicle routing. First, swapping and recharging are 2 fundamental methods to keep EVs operational during their routes. Swapping involves exchanging the depleted battery with a fully charged one, which can significantly reduce downtime. Recharging, on the other hand, means plugging in the vehicle to recharge its battery, which is more common but can take more time. Moving on, the electric vehicle, or EV, is at the heart of this discussion. As we aim for more sustainable transportation, optimizing how EVs are routed and maintained becomes crucial. To tackle these challenges, we turn to meta-heuristic algorithms, specifically the artificial Protozoa algorithm, which mimics natural behaviors to find efficient solutions. We also have 2 charging methods, which we abbreviate as EVRP/RBS. These methods help us model how charging stations are utilized in our routing strategies. When considering the types of vehicles involved, we look at the heterogeneous electric vehicle routing problem, or HEVRP, where different vehicle types are optimized within the network. This naturally leads us to the electric vehicle routing problem, EVRP, which is about planning the most efficient routes for EVs considering their unique constraints, like limited range and charging needs. Throughout this presentation, our goal is to address these interconnected challenges and develop smarter, more sustainable routing solutions for electric vehicles. Let's go over some key assumptions that shape our model. First, we assume that each vehicle departs from the depot and returns there at the end of its route. This helps us keep the operations organized and predictable. Next, we recognize that each customer has specific demands and a designated time window that must be satisfied. Meeting these constraints is crucial for customer satisfaction and efficient routing. We also consider that our electric vehicle fleet is heterogeneous. This means that each vehicle differs in load capacity, battery capacity, and energy consumption rates. Acknowledging this diversity allows us to optimize the deployment of each vehicle based on its unique characteristics. Regarding charging stations, they are equipped to do both battery swapping and recharging. This dual functionality provides flexibility in managing vehicle turnaround times and maintaining a smooth operation. We assume that the battery consumption of each vehicle depends on the travel distance and a constant energy consumption rate. So, longer trips will naturally consume more energy, but the rate remains steady. Finally, the travel time for each vehicle is calculated based on the travel distance and a constant velocity, which simplifies our timing estimates and helps us plan more effectively. All these assumptions are fundamental because they set the framework for our model, enabling us to develop efficient routing and charging strategies within these realistic operational constraints. Let's take a closer look at the constraints we're working with. First, the decision variables. These are the core elements we can control, such as which routes the vehicles will take or which customers they'll visit. Next, we have the requirement that for each customer, the number of incoming visits must equal the number of outgoing visits. This ensures that every customer is visited exactly once and that the route flows logically without any loose ends. Another important point is that each vehicle has the flexibility to visit charging stations if needed. This allows us to plan routes that can incorporate recharging stops, which is especially important for longer or more energy-intensive routes. Finally, it's crucial that each customer is visited exactly once. This keeps our routing efficient, avoids overlap, and ensures we meet all customer demands without redundancy. Now, moving on to our objective function, which is the key to guiding our optimization. It helps us find the best routes by balancing these constraints. The model ties everything together, aiming to optimize the overall route plan by minimizing costs, travel time, or other factors we've defined as priorities. By understanding these constraints and how they shape our decision-making, we can develop a routing plan that's both feasible and efficient, aligning perfectly with our overall goal of providing reliable, optimized service. Let's take a closer look at the vehicle waiting time. This is a critical factor because excessive waiting can impact overall efficiency and customer satisfaction. Managing this time effectively ensures smoother operations and reduces delays. Next, we have the concept of time windows. These are the predefined periods within which certain activities, like deliveries or pickups, need to happen. Properly aligning our operations with these windows is essential to meet customer expectations and optimize scheduling. Then, we consider vehicle recharging time feasibility. Ensuring that vehicles can recharge within acceptable time frames is vital for maintaining continuous operation without unnecessary downtime. This involves planning for sufficient charging infrastructure and scheduling. Similarly, vehicle swapping time feasibility comes into play. We want to make sure that swapping vehicles, if necessary, can be done quickly and efficiently, minimizing disruptions and keeping the flow seamless. Finally, customer time feasibility is about aligning our service times with customer availability. Meeting these time constraints is key to delivering a high-quality experience and building trust with our clients. All of these points tie back to our overall goal: creating an efficient, reliable system that balances operational constraints with customer needs. Now, let's look at some key constraints that are essential for our vehicle routing model. First, each location must be visited exactly once. This ensures that we don't waste time or resources revisiting the same place multiple times, keeping our routes efficient. Next, battery consumption is a critical factor. Since many vehicles, especially electric ones, rely on battery power, we need to carefully consider energy use to avoid running out of charge mid-route. Then, there's customer demand fulfillment, which reminds us that we must meet each customer's needs accurately, ensuring satisfaction and service quality. Vehicle load capacity is also vital. It limits how much we can carry, so our routes and loads must be planned within these constraints. All these points are interconnected. They help us develop a practical, feasible routing plan that balances efficiency, energy use, customer satisfaction, and vehicle limitations. Keeping these constraints in mind is fundamental to achieving an optimal and sustainable routing solution. Let's take a closer look at Figure 1, which illustrates the concept of artificial protozoa optimization, or APO. APO is an innovative optimization algorithm that draws inspiration from the survival mechanisms of protozoa, single-celled organisms that have evolved effective strategies to thrive in their environments. In this model, we focus on 3 key survival mechanisms that protozoa use: foraging, dormancy, and reproductive processes. Foraging, which includes autotrophic and heterotrophic behaviors, reflects how protozoa seek out resources or nutrients, and in APO, this translates into exploring different solutions efficiently. Dormancy allows protozoa to pause activity when conditions are unfavorable, helping the algorithm avoid getting stuck in suboptimal solutions. Finally, reproductive mechanisms ensure the protozoa can multiply and adapt, which in our case, helps the optimization process converge toward the best solutions. This approach is particularly powerful because it mimics natural survival strategies, making the algorithm robust and adaptable. By modeling these mechanisms, APO can effectively navigate complex search spaces, similar to how protozoa survive and thrive in diverse environments. Connecting this to the overall theme of our presentation, APO exemplifies how biological inspiration can lead to innovative computational techniques. By understanding and replicating these survival strategies, we can develop algorithms that are not only efficient, but also resilient across various problem domains. All right, let's take a closer look at Figure 2, which shows the pseudocode of APO. As you can see, this pseudocode provides a clear, step-by-step outline of how the algorithm operates. The key points here are to understand the flow of the process and how each part contributes to the overall goal. First, notice how the pseudocode begins with initializing certain variables, setting the stage for the algorithm to run efficiently. Then, it moves into the main loop, where the core logic unfolds. This is where APO makes decisions and updates its parameters. What's important to highlight is that this pseudocode encapsulates the essence of the algorithm in a simplified way, making it easier to grasp the complex mechanisms behind APO. It connects directly to our overall theme of optimizing processes through adaptive algorithms, showing how the pseudocode translates theory into actionable steps. By understanding this, we gain insight into how APO dynamically adjusts and improves performance, which is fundamental to the advancements we're discussing today. Let's take a closer look at the table showing the relationships between different protozoa numbers. You can see that the values between protozoa number 1 and 4 are quite high, around 0.99, indicating a strong similarity or connection. Similarly, the values between other pairs vary, which helps us understand their relative relationships. Moving on to the methodology section, we're focusing on APO for EVRP-RBS. The first step involves defining some initial parameters, like the population size, which we denote as PS, and the maximum number of iterations, called maxFE. There are also some special APO parameters, such as neighbor pairs, labeled as NP, and the maximum proportion fraction, PFmax. These parameters help control the algorithm's exploration and convergence. Next, in the second step, we work on representation and generating the initial population. Each protozoa or solution candidate is represented by a vector. We generate these vectors randomly at first, ensuring diversity in our starting solutions. To represent root solutions, we convert continuous numbers into discrete ones by ranking the values from smallest to largest. This ranking process is crucial because it transforms our continuous data into a format suitable for route optimization. Overall, these steps set the foundation for the optimization process, helping us systematically explore potential solutions and improve upon them in subsequent iterations. Now, let's take a closer look at the evaluation phase in our APO for EVRP-RBS methodology. After generating potential routes, the first key step is to ensure that all these routes satisfy our problem's constraints. If any route is infeasible, we need to repair it, transforming it into a feasible solution. This step is crucial because it guarantees that our solutions are valid within the problem's parameters. Next, we evaluate the fitness of each route, which essentially measures how good each solution is. In our case, we use the total traveled distance as the objective function, so the shorter the distance, the better the fitness. This helps us compare solutions objectively and identify the most promising ones. Following that, we update our Protozoa, which are the agents exploring the solution space. We apply biological-inspired mechanisms like autotroph, heterotroph, dormancy, and reproduction. These processes allow each protozoa to explore new solutions, mimic natural selection, and adapt over iterations. Finally, we update our record of the best solution found so far. We keep track of the optimal solution at each iteration to ensure we don't lose progress. The process continues iteratively until we reach a predefined maximum number of iterations, at which point we conclude the search. This methodology ensures a systematic, adaptive approach to solving complex routing problems, connecting each step logically toward finding the most efficient routes. In this slide, we're looking at Table 1, which details the specifications of the dataset EVRPTW, a benchmark instance from Schneider. As you can see, the table lists various elements, starting with stringid, which uniquely identifies each node or point in our network. The type column indicates whether it's a demand point, a facility, or a customer. Moving across, the X and Y coordinates specify the location of each node in a two-dimensional space, useful for visualizing routes. The demand column shows the amount of service required at each node. Notice that some nodes, like D0 and S0, have zero demand, indicating they might be depots or starting points. Ready time and due time define the time window within which service must begin, which is crucial for scheduling. For example, C57 has a window from 989 to 1063, meaning service must be scheduled within that period. Lastly, service time indicates how long it takes to serve each node. Most are set at 90 units, which standardizes the service process. Understanding these parameters is key because they influence route planning and optimization, ensuring that we meet demand efficiently within the specified constraints. This dataset serves as a foundation for testing and validating our algorithms in vehicle routing problems with time windows. Let's take a closer look at Table 1, which outlines the specifications of our data fleet. As you can see, we have a heterogeneous fleet consisting of 3 different vehicles. Starting with Vehicle 1, it uses a swapping charging type, meaning its battery is replaced rather than recharged on site. Its battery capacity is 74 units, and it handles a load of 100. The battery consumption rate is 0.9, and it moves at a velocity of 1, which we can assume is in consistent units. The swapping time for this vehicle is 90 seconds, and since it relies on swapping, it doesn't have a recharge rate. Moving to Vehicle 2, it recharges rather than swaps. Its battery capacity is slightly higher at 82 units, supporting a load of 200. The consumption rate is 1, and it also moves at the same velocity of 1. Here, the recharge rate is 3.87, indicating how quickly it can replenish its battery, which is an important factor in operational efficiency. Finally, Vehicle 3 also uses swapping, with a larger battery capacity of 89 units and a load of 300. Its consumption rate is 1.1, slightly higher, and it also swaps in 90 seconds. Like Vehicle 1, it doesn't have a recharge rate because it relies solely on swapping. This table really highlights the diversity within our fleet, different charging strategies, battery sizes, and load capacities. These variations are crucial because they impact how we optimize fleet operations and energy management, especially when considering the broader theme of efficiency and sustainability in our transportation system. Now let's take a closer look at the results across different customer instance groups. Starting with Table 2, which shows the initial parameters, we have 3 sets based on the number of customers: 5, 10, and 15. For each, you can see the values of F and S, which represent key initial conditions for our simulations. Moving on to Table 3, which focuses on instances with 5 customers, we observe F values ranging from approximately 143 to 316, and S values tightly clustered around 2. This suggests relatively low initial costs and consistent S values among small groups. In Table 4, for 10 customers, the F values increase significantly, from about 241 up to nearly 482, and the S values also vary more widely, indicating more diversity in the initial setup as the group size grows. Finally, Table 5 presents results for 15 customers. While the actual table isn't shown here, the pattern indicates even larger F values and more variability in S, reflecting the increasing complexity and the impact of larger customer bases on the outcomes. Overall, these tables help us understand how the initial parameters evolve with the number of customers and set the stage for analyzing how different group sizes influence the results. This ties back to our broader goal of optimizing operations across various customer scenarios. All right, let's take a look at the optimal routes we've identified. On this slide, you'll see 3 different routes labeled for clarity. First, we have route C208C15, which is highlighted in Figure 5. Then, there's route R201C10 shown in Figure 4, and finally, route RC108C5 in Figure 3. The key point here is that these routes have been carefully analyzed to determine the most efficient or optimal path based on our criteria, whether that's time, distance, or other factors. What's important to remember is that each of these routes represents a solution tailored to specific conditions or constraints we've considered throughout the presentation. By comparing these options, we can see how choosing the right route can significantly impact overall efficiency and effectiveness. This concept ties back to our overall theme of optimizing operations. It's all about making smarter choices to improve outcomes. So the takeaway is that selecting the optimal route isn't just about finding the shortest path. It's about balancing various factors to achieve the best overall result. All right, as we wrap up, let's revisit the key points from this slide. The heterogeneous electric vehicle routing problem, or HEVRP-RBS, was specifically formulated to minimize the total distance traveled. This is crucial because reducing travel distance not only saves energy and costs, but also enhances efficiency and sustainability. To tackle this complex problem, we employed the Artificial Protozoa Optimization, or APO, which is a nature-inspired algorithm. What's exciting here is that our computational experiments showed APO was actually able to find the optimal solution for HEVRP-RBS. This demonstrates the power and potential of using bio-inspired algorithms in solving real-world routing problems. Overall, this connects to our broader theme of leveraging advanced optimization techniques to improve electric vehicle logistics and promote greener transportation solutions.